In the case of a parallel circuit is where resistors start and end at the same voltage or height. In other words, the resistors are directly connected at the top and at the bottom with no other resistor in between. Which circuit shows resistors in simple parallel? This is called parallel. So we know that whatever loop we take, we have to use up the same amount of voltage. So we have a simple parallel circuit when each of our resistors will use up the same amount of voltage. In other words, our charge has a choice of going down this path, or down this path in order to make it back to the battery. So what I'm looking at here, this would be a simple parallel circuit. And this is a combination parallel series circuit, because although I do have one choice between the two paths, in this path there are two resistors that I would have to go through if I choose that path. In other words, these two resistors are in series with each other, but in parallel with this other resistor. So they're in series with each other because once I choose this path, I have to go through them both. But they're in parallel with this resistor because I can choose to either take this path or the other path. So this is a combination series parallel circuit. Example number 6, find an expression for the total resistance of a parallel circuit. So again, we're going to work with Kirchhoff's laws, and Kirchhoff's voltage law says if I have a total voltage here, let's call this again resistor 1, resistor 2, resistor 3, then the amount of voltage I start with here, I have to use all of it up no matter which path I take. In other words, the total voltage is equal to the voltage drop across resistor 1 is equal to the voltage drop across resistor 2 is equal to the voltage drop across resistor 3. If you had more, each of them has to have the same voltage drop because I have to use up all my energy before I get back to the battery. On the other hand, Kirchhoff's current law says we're going to split our current at each of these junctions. We don't know how much is going to go each direction until we have numbers that we add on here, but the basic idea is that the amount of current that I start out with, call that my total current, has to split between these three paths, and it all has to make it back to the battery. In other words, the total current is equal to the sum of the current through each resistor. Convince yourself of that. If I started out with 5 amps here, this is just a quick example, and 2 amps went this way, and then 3 amps are here, and then maybe 1.5 amps went this way, and 1.5 amps went this way. The total current through all the resistors has to add up to give me my total current that I started with. And again, with those two ideas, we can come up with an expression for the total resistance. So in this case, I'm going to substitute V equals IR, or in this case actually I equals V over R, into my current law. So I total is going to be V total over R total, and that's going to be equal to V1 over R1 plus V2 over R2 plus V3 over R3. And again, like the last time we said, well, these guys are actually all equal, so let's just call them all VT. So instead of V1 is equal to VT, V2 is equal to VT, V3 is equal to VT. And again, like we did in the last time, we can actually divide each of these terms by VT. So what happens then is our expression isn't quite so nice as we had in the first time round. These guys all cancel, but they all leave 1s at the top. So all our r's are still in the denominator. They don't just magically turn out to be in the numerator. So what I have is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus, you get the picture, we're looking at the reciprocal of our resistances rather than a straight addition, which is going to lead to some interesting problems. So let's throw some numbers on there and see what we get. So let's say we have R1 maybe being 10 ohms, and R2 also being 10 ohms, and R3 being 20 ohms. So to find the total resistance of this circuit, this is 1 over R total is equal to 1 over 10 plus 1 over 10 plus 1 over 20. So you might need to use your calculator to add that up, or if you want to give them all common denominators, this is 2 over 20 plus 2 over 20 plus 1 over 20 is going to be 5 over 20 is 1/4. And then to actually find your total resistance, to get this to the top, we need to actually take the inverse or reciprocal. So we're going to raise this side to the -1. This is going to give me just our total. Flip it over. This -1 flips it over. And when I do that, I can also flip this over and be like, oh, the total resistance is 4 ohms. And again, that's kind of nice. Turns out to be a nice even round number. Doesn't usually work out quite that nicely. So what that means is equivalent circuit would have a 4 ohm resistor replacing all of these resistors. Now what you might have noticed in the last example is that when we added them up, our total resistance was higher in a series circuit than on any one resistor. For a parallel circuit, your resistance will always be lower than on any one resistor. So I've got my 4 ohm resistor instead of these 3 together, which kind of counterintuitive that you end up with such a small resistance, but there you have it. So to add in a few more numbers, let's say that we happen to hook up a 36 volt battery. So again, in my equivalent circuit, I've still got a 36 volt battery, 4 ohm resistor. So to find my total total current, I'm still looking at total voltage over total resistance. So 36 over 4 would be 9 amps. So these 9 amps start out here, but they're going to split as they go through each resistor. So in the case of each resistor, we can use the total voltage. We actually know if this is 36 volts, we start out with 36 volts, we have to use them up no matter which path we take. So this is also going to be 36 volts. It's also going to be 36 volts. Also going to be 36 volts. So to find the current at each place, we just take the voltage divided by the resistance. So 36 divided by 10 is 3.6 amps. 36 over 10, 3.6 amps. And 36 over 20 is 1.8 amps. And if you add these all together, you should get back your 9.0 amps total that you started with. So that is resistors in parallel. Kind of counterintuitive, but it works out with the voltage law and the current law saying the voltage has to be the same across all 3, and the current has to add up to the total current. So again, here's our little summary. We've got parallel, resistor, and what we usually write, it's kind of a little bit faster, is to say 1 over R1 plus 1 over R2 plus 1 over R3 plus however many that you have in parallel. Inverse is going to give me my total resistance. And again, resistors are measured in ohms. Example number 7, find the total resistance, the total current, and then find the voltage and the current for all resistors. So total resistance is going to be the inverse of 1 over my first resistor plus 1 over my second resistor plus 1 over my third resistor, inverse. Now it'd be nice if this inverse could just flip each of these fractions individually, but it doesn't quite work that way. We actually have to find the sum of the fractions first, and then take the inverse. So go ahead and type that into your calculator. 1 over 10 plus 1 over 15 plus 1 over 20. Inverse that to the power of -1. And that tells me, well, my calculator gives me an exact fraction of 60 over 13. Now that might be useful to us when we're doing further calculations. When we're giving an answer, we are going to turn that into a decimal, which is 4.62 ohms. But because I'm going to need to use that number to calculate the total current, I'm also going to keep it as a fraction to refer back to. So then I need my total current, which is going to be the total voltage divided by the total resistance. Total voltage, in this case, 60 volts, divided by 60 over 13. I think that's going to pop up just to be 13 amps exactly. If you had rounded it, then you won't get an exact number, which is a little bit annoying to work with later on. So that means I have 13 amps leaving my battery. And when it comes to the first junction, it's going to split. And I don't know exactly how it's going to split, so I'm going to find current actually last. And first I'm going to find the voltage for each resistor. So the voltage is going to be the same across each of my paths. So if I have 60 volts here, I'm going to have 60 volts here, 60 volts here, 60 volts here. Put a decimal in to get me 2 sig figs. And then I know that current equals voltage over resistance. So voltage over resistance, this is going to be 6 amps going here, 4 amps going this way, 60 over 15, and 60 over 20, 3 amps going this way. And again, if I add them all together, I should end up with my 13 amps that I started with. So this is a simple parallel circuit, and there you have it in one more example. So now we're taking it the next level up with a combination series parallel circuit, because no longer do we have everything in parallel where you would go through either this one or this one or this one or this one, and we don't have everything in series as in we have to go through every single one of them. What we're looking at is parallel branches. So you could go through the 10 or the 15, come back, then you go through the 20 or the 5, come back, and then you go through the 12 or the 12. So we do have parallel options, but we have to go through one of each of these options. So we've got parallel branches, but the parallel branches are in series with each other. So how in the world are we going to handle something like this? Well, again, we're going to make use of both kinds of adding resistance, the series adding of resistance and the parallel adding of resistance. So for each of the parallel branches, we're going to take them one at a time and add them using our parallel rules. Because the 10 and the 15 are in parallel with each other, we can replace them with one equivalent resistor by finding their equivalent resistance. So for branch number 1, my resistance is going to be equal to, using the inverse rule, 1 over 10 plus 1 over 15 inverse, because the 10 and the 15 are in parallel with each other. So plug that into your calculator and figure out the equivalent resistance. And when you type that in, you get an equivalent resistance of 6 ohms. In other words, we could take out these 2 resistors and replace them with one resistor of 6 ohms. So when I draw my equivalent circuit down here, comes up, I'm going to replace those 2 resistors with one resistor with 6 ohms. And then I'm going to do the same thing for this branch. This is called this parallel branches number 2. Again, I want to find the resistance, which is 1 over 20 plus 1 over 5 inverse. Again, type that into your calculator, and that gives me an equivalent resistance of 4 ohms. So I'm going to replace these 2 resistors with one equivalent resistor of 4 ohms. Then do it again one more time for this last parallel set. Find the resistance. And you might think, oh, 12 and 12, maybe it'll just be the same. Or, I mean, if they were in series, you would just add them. But it turns out that it's actually going to be half. When you add 2 resistors, 1/12 plus 1/12 is going to be 2/12. And then when you flip it over, 12 over 2 is just 6. So this is going to give me a resistance also of 6 ohms. So I add that equivalent resistor, swap it out for my parallel branch. This is another 6 ohm resistor. And now looking at this equivalent circuit, we swapped out each of the parallel branches for their equivalent resistance. Then we see, oh look, now what we've got are 3 resistors in parallel. So to find the total resistance of those ones, we just add them up straight up. So R is going to be equal to 6 plus 4 plus 6 equals 16 ohms. So again, this would be equivalent to having one circuit with one equivalent resistor of 16 ohms. So how does that help us to find the voltage drop across each resistor in our original circuit? Well, let's try working backwards from this circuit. So what I have got going on here, I've got this 5 amps of current. That is my total current that comes out of the battery. So I'm going to put that on this circuit as well. This is going to be 5 amps, which means I can use this circuit to find the total voltage. Because if this is an equivalent resistor to this, it has to use up all the voltage that each of these use. So if I've got 5 amps here and 16 ohms, to find the voltage total, I know it's going to be the current total times the resistance total. So that's just going to be 5 times 16, which is going to be a total of 80 volts. So my total total voltage, 80 volts, is going to be true on each of my circuits. So this 80 volts is 80 volts. It's the same cell. I haven't changed the cell or the battery in each of my circuits. And this 5 amps is also going to be true for this equivalent circuit. So 5 amps will let me figure out how much voltage is used in these branches. Remember that the amount of voltage used in each branch is going to be the same, because no matter which path I choose, I have to get back to the battery using all my 80 volts. So I can use my current to figure out how much voltage is used in each branch by using the equivalent resistance of 6 ohms. So for this one, again, I know voltage equals current times resistance. So current times resistance, 5 times 6 is going to be 30 volts used up here. This 5 amps also goes through the equivalent 4 ohms. So 5 times 4, it's going to be 20 volts here. And the 5 amps comes back around. 5 times 6, again, is 30 volts down here. And these 30 volts are used in each branch of my original circuit. So if this 6 ohm equivalent resistance to this uses 30 volts, that means this 15 ohms also uses 30 volts, and this 10 ohms also uses 30 volts. If my equivalent 4 ohms to the 20 and the 5 uses 20 volts, then in each branch, I've also got 20 volts being used up, each branch. And the rest of the 30 volts being used up down here. So that means whichever path I take, I should use a total of 80 volts by the time I get back to the other end of the battery. So if I go this way, 30 volts plus 20 volts plus 30 volts gives me 80. So again, whichever path I choose has to use up all 80 volts that I started with. Then to find the current in each of these, I now have 2 pieces of information. I now have the resistance and the voltage, so I can calculate the current using Ohm's law. So I equals V over R, voltage over resistance. So 30 over 10 is going to give me 3 amps going this way, and 30 over 15 is going to give me 2 amps going this way. And these 3 plus 2 amps do add up to give me the 5 amps that I would expect. So that's good. That means I'm being internally consistent. Here I have 20 volts divided by 20 ohms is going to be 1 amp. And 20 volts divided by 5 ohms is going to be 4 amps. And again, 4 plus 1 gives me the total of 5 that I want coming in, 1 and 4 coming out. And last but not least, I've got 30 over 12 in both cases. 30 over 12 is going to give me 2.5, I should have guessed that, 2.5 amps going each direction because it splits exactly equally. So 5 amps comes in and it goes equal directions because we have equal resistance. So we've got half of it going each direction. So it should be consistent with all the different rules that you know. Ohm's law should work every time. Kirchhoff's voltage law should work every time. And Kirchhoff's current law should work every time, no matter how you find your numbers, whichever rules you're using. So in parallel branches, I can use my parallel rule to find equivalent resistors. And then once I've got those, I can use my rule for series to find, again, an equivalent resistor to replace the ones that I'm working with. So, example number 8 illustrates an important point. it shows us that the voltage drop across parallel resistors is the same as the drop across the equivalent resistor in the equivalent circuit. So we use that rule to say, well, if I have a 30-volt voltage drop here, then I must have 30 volts in each branch of my equivalent parallel circuit. So that's a very handy rule. In household circuits, plugs and lights are wired in parallel to 120-volt alternating current. Each circuit has a circuit breaker in the circuit. And the circuit breaker is an automatic switch that opens when the current exceeds a set value, usually 15 amps. When the switch is opened, no more current flows through the circuit. Example number 9, if we connect to a 1200 watt hairdryer and a 500 watt TV in the same circuit, will we cause a 15 amp breaker to trip? In other words, will the current, the total current here, be greater than or less than 15 amps based on the 120 volt power source? So what we want to be able to calculate is how much we're looking at for current for each of them in order to figure out what the total current is going to be in the circuit. So we are told 1200 watt hairdryer. That's going to be the power used by the hairdryer, and a 500 watt TV. Again, we're given the power. So I've got, this is going to be 1200 watts. Hairdryer uses a lot of power, and 500 watts for the TV. And because they are in parallel, and I've got 1200 volts coming out of here, I've got to use 1200 volts no matter which way I'm going. So this has to be 1200 volts here and 1200 volts here in order to complete the circuit. So I get 1200 here, lose 1200 if I go this way, lose 1200 if I go this way. And so how does that help me find the current? Well, I know that power is equal to current times voltage. So then I can rearrange this to say, well, current then must be power over voltage. So I can find the current that each of these is going to draw. So power over voltage, 1200 divided by 120 is going to be 10 amps here. And 500 divided by 120 is going to give me 4.17 amps here. So if I got 10 amps coming down this way and a 4.17 coming from this direction, then I'm going to end up with 14.17 amps total by the time I get to the circuit breaker. And in that case, because our circuit breaker trips at 15 amps, it would break the circuit at 15 amps, and we're under that. No, we will not cause the circuit breaker to trip because we are under 15 amps. So that's it for this lesson. Good luck on the homework and on your mastery quiz.